All right, we are recording.
Hi, Guillermo.
Hi, Guillermo. All right, so let's go over the packet.
Here, did you do the packet?
Oh, God.
No.
He used to be such a good student.
Used to be.
Yeah, used to be.
Some award you got. Huh? Kidding.
All right, so we're doing the equivalent one-body problem where we replace our two bodies orbiting their common center of mass with a reduced mass orbiting the combined mass of the system. And so let's remind ourselves of how center of mass works. So if we have mass 1, mass 2, and we draw the position vector of mass 1, and we draw the position vector of mass 2, so R1 and R2, then we can also draw in the relative vector, the relative position vector. In other words, the position vector of M2 treating M1, the instantaneous location of M1 as the origin. So that would be what in our equivalent one-body problem is going to be what we're going to call R, and that vector is the displacement of mass 2 relative to mass 1, so R2 minus R1, where M2 is relative to M1. If you are riding along with M1, what vector would connect you to M2? That's what R represents. And remember that the definition of the center of mass for our two-body system is, we'll call it R, is equal to, by definition, M1 times R1 plus M2 times R2 divided by the total mass, M1 plus M2. And that always lies somewhere along the line joining the two particles to one another. So in other words, it would be somewhere along that vector R that connects the two particles. Where exactly it will be will depend on what the two masses are. The bigger one mass is compared to the other, the closer the center of mass is to just being where that mass is. So the center of mass of the Sun-Earth system is very close to the center of the Sun, for example. But if you had two Earth-type objects orbiting one another, the center of mass would be halfway between them. So the center of mass is closer to the larger of the two masses. It does lie along the line joining the two particles. So that vector capital R that connects the origin to the center of mass is the position vector of the center of mass, and it's M1R1 times M2R2 over M1 plus M2. And if we have n particles, more than two, then we just generalize this in the natural way. We just add up all the miRi's and divide by the sum of all the mi's. So we would have capital R is the sum from I equals 1 to n of miRi. Divide that by, sum, I equals 1 to n of all the mi's. So if there are three particles, it would be M1R1 plus M2R2 plus M2R3, M3R3 over m1 plus m2 plus m3, for example. And in that case, there's no longer, there's lots of lines between the particles, and it doesn't lie anywhere along any one of them necessarily. So it's just somewhere within the distribution of particles. But again, if one of them is really a lot more massive than the others, the center of mass will lie close to its location. The solar system's center of mass lies close to the center of the sun. It actually lies outside of the center, outside of the sun's surface, because of the influence of Jupiter and Saturn primarily. But certainly it's a lot closer to the sun than it is to any of the other individual planets. But the sun, in fact, its center moves around the center of mass of the solar system under the gravitational influence of all the planets. It can't be that the sun is just sitting there with the planets orbiting it, because the planets do exert forces on the sun, and sun big, but not infinitely big, and so it does have to move. Well, another way to put this is if you call the bottom there capital M, the total mass of the system. In classical mechanics, mass is additive. Remember, in relativity, it ain't. But in classical mechanics, mass is additive. Then this says that capital M times R of the center of mass is equal to the sum of the MIR. And it gets tiresome to keep writing the sum from I equals 1 to n, so from now on we'll just write sum I for the summation over I. It's understood it goes from 1 up to the number of particles in the system. Time to differentiate, where we'll use the dot notation. You guys familiar with that? Put a dot over something, it means the time derivative. So we will, have you seen that notation before?
Sounds familiar.
Sounds familiar, okay, trust me on this, yeah. So like x dot would be dx dt, y dot would be dy dt, and so forth. If you haven't heard it before, it's very simple. X dot would be dx dt, y dot would be dx dy dt, and so forth. Dot means time derivative. So we're going to take the derivative with respect to time. Thus, mr dot, which of course has 3 components because it's a vector, mr dot will be the sum of the mi ri dot. We're assuming the masses themselves stay the same. These are particles that are not shedding or gaining mass. Or, if we call capital V the velocity of the center of mass, then that says that m times capital V, and I'll emphasize that it's a capital by putting little serifs along the top of it there, mv is equal to the sum of the mivi, the velocities of all the individual particles. But in classical mechanics, mv is what we call the momentum of the particle, where we use the notation p for momentum because of the fact that there aren't any p's in the word momentum, and therefore we should use p to represent it. So this would be the sum of all the momenta, the pi. Say, okay, well, capital, the sum of the momentum of all the particles would be, the momentum of all the particles would be the total momentum of the system. And notice that's just the total mass times the velocity of the center of mass. So the system as a whole has a momentum that would be the same as a particle with the mass of the whole system moving with the velocity of the center of mass. So with P equals big MV, we see that in terms of finding the system momentum, we can replace the system with a single particle of mass big M moving with the velocity of the center of mass. Well, that's a nice result. Okay, any questions? I'm sure it's going. Yep, it's going. Flash, flash, flash. Yep, Gio's still with us.
Yes, still awake.
That's right. So, 2, 4, 6, 8. Time to differentiate again. So maybe it should be like, what would it be like? 4, 8, 12, 16. Time to differentiate. Isn't that keen? I guess. I don't know.
Close enough.
Close enough, right?
Give it the good old college try.
What?
Give it the good old college
Good old
try.
college try. That's right, yes. It could be worse. Another differentiation yields P dot, big P dot, will be the sum of all the little pi dots. Since big P is the sum of the little p's, then big P dot is the sum of the little p dots. But Newton's second law says what is equal to the rate of change of momentum of a particle? What?
I was writing
So Newton's second law says that what is equal to the rate of change of momentum of a particle? Mass times acceleration is the rate of change of momentum for sure, right? Because if I take d dt of mv, well that is mv dot, right, which is p dot. Of course, another name for v dot is a, so ma is p dot. You'd probably more instantly recognize that ma would be equal to the what on the particle?
The force.
The force on it. So force is rate of change of momentum is another way to state Newton's second law. In fact, it's more fundamental than ma. So this is the sum of the forces on all the particles. So this says rate of change of system momentum equals total force on the system. If I add up the forces on all the particles, that's the total force on the system. Now for each particle, the total force on it will be a combination of any forces exerted on it by other particles in the system, plus any forces exerted on it by particles that are not part of the system, by the rest of the universe, if you will. What do we know about those internal forces? In other words, if I have two particles exerting forces on one another, Newton's third law says what about those two forces that the two particles are exerting on each other? Equal and opposite. So in other words, internal forces cancel in pairs, because any forces that the particles exert on one another obey Newton's third law, equal and opposite. So the sum of the internal forces adds up to 0 because they cancel in pairs from Newton's third law. So by Newton's third law, for a closed system, a closed system means only internal forces, no external forces applied. There's no such thing as a truly closed system because the Andromeda galaxy is exerting gravity on any system. So is that galaxy 3 billion light years away, etc. But under many conditions, we can assume that those forces are negligible. But for a closed system, only internal forces, no externally applied forces. The internal forces cancel in pairs. Well, that's true for an open system too. The internal forces always cancel in pairs. So I guess I should say, since the internal forces cancel in pairs, so that in that case, the sum of the Fi is equal to 0. It wouldn't be 0 if there were externally applied forces, because then those are not canceled out for our system. Of course, if we drew a bigger box and included whatever is exerting the external forces as part of the system, then we still then get back to another closed system again, but whatever. We have that P dot is equal to 0, because P dot is the sum of the forces, but if there's only internal forces, if we have a closed system that's only interacting with itself and nothing else, then P dot is equal to 0. Capital P dot, the system momentum dot, is equal to 0. So what does that say about the system's momentum? If P dot is 0, the momentum itself is. If the derivative is, yeah, it's constant, right? If the derivative is 0, then the quantity itself is constant. So P, the system momentum, is constant. Momentum conservation, in other words. If there's only internal forces, if there's no external forces, the total system momentum stays constant. And that says V is constant because the total mass doesn't change, it's just the sum of all the masses. So that says the center of mass moves in a straight line at constant speed. Mass moves in a straight line at constant speed. As long as there's no externally applied forces, center of mass moves in a straight line at constant speed. So if you were out in space, far from any stars and planets, so there was no significant externally applied gravitational force on you, and you decided that, or somebody threw you or whatever, you're flying along, then you can do all the pirouettes you like. Your center of mass, despite all of your acrobatics, just flies along in a straight line at constant speed. There's nothing you can do to change that because any part of your body exerts an equal and opposite force on any other part of your body. When you consider them exerting forces on one another, you cannot exert a net force on yourself, and so as a result, your center of mass will move in a straight line at constant speed. Now, if you were carrying a bowling ball, you could throw the bowling ball, and in that case, the center of mass of you and the bowling ball proceeds to continue moving at a straight line at constant speed, because you can consider the system to be you and the bowling ball. But you yourself then, as a subsystem, well, now you can change your direction by throwing that bowling ball, because you've transferred momentum to the bowling ball, it transferred equal and opposite momentum to you, and so that's how you can change your direction. That's how rockets essentially work. You blow some gases off with the rocket nozzle and transfer momentum to those gases, and so therefore momentum is transferred to you. So if you've got a jetpack, you can fly around, do different things, and so forth. But if you keep the system always being the same set of particles it was initially, you and the molecules that are in the jetpack before you fire them out, the center of mass of that is always moving in a straight line at constant speed. You get to draw a box anywhere you like and call it the system. If you're consistent and keep the same particles as the system the whole time, it's always going to move in a straight line at constant speed if it's a closed system. On the other hand, if you're considering yourself to be an open system, there is external force on you. For example, you go up on a diving platform and then you jump off. And, well, in that case, Earth is exerting a gravitational force on all your particles. So in that case, what we find is that the rate of change of the system momentum is equal to the net gravitational force exerted on you by the Earth. And what we conclude from all of this is that the center of mass moves in exactly the same way that a single particle would, having the same mass as you do with the force applied on it being the externally applied force, net external force on you. So, as I would hope you realize, somebody who dives off of a diving board can do all kinds of whatever they like. What trajectory does their center of mass follow? It follows the same trajectory that a bowling ball would, or whatever, a single particle would that has that same gravitational force applied.